6. Denny is coming. Hello, Denny. Okay, we can start a bit early. Finish 5 minutes early then. Good. Okay. That is your handwriting? Okay. 1, 2, 3, 4, 5, 6, 6. Okay, good. Alright, welcome everyone. Why am I playing up again? Okay, following. Just checking. Okay. All right, so we are going to finish off the chapter 4 and then move on to chapter 5 today. Okay, so before we actually move on to that, okay, give us a quick revision on module 6. First of all, okay, so giving you some general ideas about what we're learning in the module 6 now. So acid and base reaction is the whole module chapter that we're learning about acid and bases. Now let's start from this. There are various ways we can define the acid and base. Well, you only probably need to just do 2 for now. One is the Arrhenius definitions of the acid and base. Okay, Ashley, what's the Arrhenius acid? Release. So acid is something that release what? Release hydrogen ion when it's reacting with the water. Okay, what about base? It's something that release again? Release hydroxide ion too. Okay, so even though this is kind of outdated due to there's some limitations, so let's talk about the limitation of that. Arrhenius has a few the limitation. One is that it's only works in the aqueous with the water, presence of water too. So it's a good model, it's a good definition too when we're describing with the solutions forms too, but sometimes we have the gases like all the some solidified acid too. I wasn't able to explain that all too. And because of that, the example of that is NH3. Ammonia gas is working as the base, and as it releases the hydroxide ion, but this could not explain why. Okay, so we have a new definition from Bronsted, Laurie, to scientists that they define that acid is now be a hydrogen ion or proton donor, and in base is something known as hydrogen or proton acceptor. So nowadays we're taking more of this Bronsted and Laurie definitions too. So using that definition, we can explain quite a lot of the more of the variety of the acid and bases. So for example, we know that hydrochloric acid is an acid. when this is reacting with the water, H2O liquid there, and so show the single arrows there too. This is an acid, that means it's a releasing, the donor is releasing the hydrogen ion. So from that, the hydrogen ion H plus will be donated to the water, becomes 2. We have a hydronium ion H3O plus, and the chloride ion is formed as well too. So this is what? This is working as a base this time, as it's working as a proton acceptor, and this is working as an acid, that is a proton donor too. And one thing about using the benefit of using the Bronsted-Lowry is we can define as something known as the conjugate acid and base pairs of them two. Now, simply conjugate means the next two. So when we say conjugate, it means that having one hydrogen ion differences. So hydrochloric acid, for example, is your acid. HCl is an acid. Then the base, conjugate base of that must be like having lost one hydrogen ion. That Cl minus is a conjugate base of the hydrochloric acid. Okay. What about water? Water, it can be working as, so water can be working as an acid. Think about it, working as an acid. Okay. Means that it is ready to donate the hydrogen ion. So after you donated it, it becomes to the hydroxide ion. So these two, you will see only one hydrogen ion differences, which is conjugate base. Okay, water can also be working as, I'll write it this way, working as a base. That means we have a hydronium ion that's working as an acid and conjugate base, or say base or a conjugate acid of that too. Now, the rule you have to remember about conjugate acid and base, that we just something that related today is, it's good to remember that the conjugate acid of weak base is always be strong acid. Okay, let's think about what I mean by the strong and the weak. So when we define the strength, strong versus weak, you remember that we define the strong as that is 100%. It's not 99, 90 point. It's always be 100% or fully dissociating. Or sometimes using that ionizing. Okay, so it's not like in a few percent. It's always 100%, which means if I have hydrochloric acid, say 1 mole of the hydrochloric acid, if I have 1 mole of the hydrochloric acid, all of those will be ionizing or dissociating. You can think about dissociating like kind of divided into the hydrogen ion and the chloride ion like this. It will be same concentration 1 mole to the 1 mole. So in the case of the concentration strong acid, we tend to say that has the same concentration of the hydrogen ion, okay, or have the same concentration of the hydronium ion for the monoproteiony, by the way. Okay, for the weak acid and base, it would be partially dissociating. The meaning of the ionizing the water. So partially means what? It's not 100%. It would be like, but when we say partially in chemistry, I'm saying like it would be something less than 1% even. Think about what you mean by 1%, less than 1%. That's like if you have 100 of the, say, example, the acetic acid is a weak acid. If I have hundreds of the acetic acid, maybe one is willing to donate the hydrogen ion. Rest of the 99 will be remain as the some acetic acid. Does it make sense to you? Okay. Sorry, I just shared that link to Donna and come back to you. Copy this down because it's a good summary of everything that we're learning through. Yep, so this is the only case that this definition can be only used using the Bronsted-Lowry. We can't use the Arrhenius to describe that, so bear in your mind for this. Okay, so going back to this, then we can understand the formula here. Conjugate acid of the weak base is now known as strong acid. Let's think about what I mean here. An example of the NH3. Ammonia is a weak base, so this is a weak base. Then what would be the conjugate acid of this weak base then? NH4 plus. Having one hydrogen, so conjugate acid of that. So which means that when we have the conjugate acid of the weak base, we take that as, oh, this is working as a strong acid, sorry. It means what? It's going like 100% dissociating the hydrogen ion. So when we're thinking about the reaction between NH4 plus with the water, H2O, we show that in the single arrows like this, it's going one directions only, and doing what? This is working as a now strong acid. Water is kind of accepting that, so it becomes 2, and hydronium ion, and leaving that the ammonia like this. Does it make sense to all? Okay. And we also learned about something. Oh, no. Let's do the opposite one too. That means if you have a conjugate base of the weak acid, we can reinterpret that as this. It would be strong. That would be strong base. So example of this, we can think about acetic acid. Joanne, this is a weak acid, yeah? What would be the conjugate base of this then? Which is acetate. That's a conjugate base. We take that as, because it's the conjugate base of the weak acid, we take this as the strong base as well too. So when the acetate then reacting with the water, H2O, that tends to be accepting the hydrogen ion, forming that acetic acid again, and leaving that hydroxide ion here like this too. Okay, so good thing to remember, this is a key point that we're going to use and used in the buffer solutions as well too, and some titration as well. Any questions up to this point here? Okay, now Ka and pH calculation, something that we have learned before too, so I hope you're looking at revising that, because you will get the questions in your topic test next week as we're going to go through that. Okay, so for now, can you just kind of memorize that? The conjugate acid of the weak base working as strong acid, conjugate base of the weak acid would be strong base, but like some sort of like a formula that you can use. All right, why? Because we're going to use to determine that the pH curve, the titration curve that we learned last week. So let's start off from in chapter 4, the volumetrically analysis. Let's kind of finish that up and then move on to the buffer today. So page 164, please. Last week, we did some titration using the burette and pipette. Remember the techniques that you have to use the pipettes as well too. If you're doing the practical tasks in the schools, you need to actually use that techniques again and again. Next week in the practical task, you will be given, I'm going to divide the groups into 2. So first group and second group will do the same experiment, but there's different time. You will only get 40 minutes for the practical task, and within the 40 minutes you need to complete the titration, and you need to solve the question as well too. So you will find that it's quite intensive actually solving that question in the exam conditions too. But the purpose of that is I want to give you like some thought about how to prepare that too, or like put yourself into the examination conditions too, so you can prepare the practical task better if you have one later. All right, let's go through some titration pH curves. That's something we kind of touched it. All right, we can have the titration curve between strong acid and strong base. Do you remember that? How do we know it's a strong acid and strong base? In general, like they are shown in the higher or the lower pH values too. So in case of that, we started from the strong base on the top. Okay, means the pH meter is kind of inserted into the conical flask. we're measuring that and we describe this region as kind of buffering region. Remember this for now. We come back to this after we complete a buffer today. And then what you see there is the equivalence point. Now, Oren, what is the equivalence point?
It's like the amount of like acid and base needed to neutralize the reaction.
In other words, the concentration of the hydrogen ion and concentration of the hydroxide ion in the same. So equal amount, equal like a level concentration of that too. Judy, what about the end point? So if the equivalence point is point where the concentration of the hydrogen ion is the same as hydroxide ion, or the neutralization point, that's what we're looking for. What does it mean by the end point that we used last time? Not too sure, okay? End point is a point where we see the permanent, the color change of the indicator. So for example, the end point of the phenolphthalein that we use, and then you see like bright pink color changes to, it would be somewhere between like a 9.2, 8.2 to 10. Okay, you actually see the permanent color change to pink during the titration. So we call that, when you see the indicator like change the color permanently, we call this end point. We see that no further color changes from it. But it doesn't mean that the end point is always the same as the equivalence point. This is why you need to select the suitable, like the most suitable indicator, that we want to match the end point to your equivalence point. When you see the permanent color change, in other words, okay, when you see the permanent color change the indicator, that's indicating the equivalence point. So that's the importance of choosing the right indicator. So if we know the type of the titration, or if we know the type of the acid and base you put it in, that means we can predict its equivalence point. So for example, the strong acid and strong base, they are having the pH equivalence point of this 7. In other words, you need to choose your indicator that change having the end point at pH 7. That'll be either be bromothymol blue or thymol blue, or like last time, we can use phenolphthalein, but in this case, we're looking for the pale pink color rather than the bright pink color changes too. Okay. Important to think they're producing something known as neutral salt. Highlight that in here. Today we're going to talk about some of the salt types. So we will have different type of salt. The salt in chemistry, I probably explained that before too, it doesn't mean like a table salt or having a saltiness or the taste. This means the ionic compound. Ionic compound means what? It's a combination between the metal and non-metal. So we can have something a neutral salt, we can have the acidic salt, we can have the basic salt. Then how to determine like whether that's a neutral, acidic, or basic? So to determine that, what you need to do is you put that into the water. You put those salts into the water and you look for what products they are forming. Okay, so neutral salt has an example of this. Sodium chloride is a neutral salt. So think about the sodium chloride. If we put that into the water, H2O liquid, okay, we produce what? It produces what? Because sodium chloride, have a think about whether they are accepting or donating any of the hydrogen ion from the water. It doesn't really do, because as we learn from the solubility, water kind of helping that breaking the bond between sodium and chloride, it's making this sodium chloride AQ instead of the solid. Which means you wouldn't see no change in the pH at all. Because having the more salt, like the table salt, doesn't mean that you have a more acidic solution or the basic solution in that. This is how we know whether that's acidic, the neutral salt. So how do we know from that? Have a think about the property of the sodium and chloride, whether they will be accepting or donating the hydrogen ions. None of those, sodium and chloride, will not really welcoming to. Same for the nitrate. Okay, nitrate would not actually accepting or donating the hydrogen ion too. All right, move on to the next titration. Let's go on. When we have the titration between weak acid and strong base, you actually see that Because it's strong base, think about the meaning of strong base. It's 100% dissociating. It's dominating the whole titration process. So what does it do? It's kind of lifted up the equivalence point from 7 to the higher than 7. So it's giving us that clue that, oh, as we have the equivalence point somewhere around 8, or sometimes be 9, the suitable indicator we generally use for this type of titration is the phenolphthalein, which has the pH range of the 8.2 to 10. We can also use some other things, but generally we use the phenolphthalein for this case too. Now, interestingly, you will see this. When the weak acid is reacting with a strong base, it's producing the basic salt. Basic salt. So in the example of that, when we have acetic acid that's reacting with the sodium hydroxide, that's forming the sodium acetate. So let's think about the basic salt in here first. So we have sodium acetate. Sodium acetate in here like this. Actually, have a look at don't worry about the sodium here, just look at the acetate. Would this be any of the conjugate acid or base or something? This one? It's a conjugate base of acetic acid. Is acetic acid strong or weak? It's a weak. So can we say this is a conjugate base of the weak acid, isn't it? And we just learned that in here. When we have conjugate base of the weak acid, that's working as a strong base. Okay, just remember as a kind of formula, it's giving a clue that, oh, we have a weak acid, sorry, the conjugate base, that means it's working as a strong base. It's working as a strong base now. Means that when this is reacting with the water H2O, putting that into solid, assuming that we have a solid of that, what happened is this will now working as a strong base. Remember what the base, according to Bronsted-Lowry, it's a proton acceptor. It's accepting the proton from the water, forming that acetic acid, and then leaving that sodium and the hydroxide. Or the sodium hydroxide in the sum of 2. Most important thing is you to see that hydroxide is formed in that mixture of that acetic acid. Now, presence of the hydroxide means that it will affect the pH dramatically. That having the greater amount of the hydroxide in the solution means what? It will increase the pH. So this is why we call this as a basic salt, making that when we put the basic salt into water, you will see that they will produce the hydroxide ions, or making the solution to be water to be basic, or increase the pH. The same thing basically. Does it make sense to all? Okay, that's how we can identify the difference between neutral to the basic salt. And the basic salt can be produced when we put the weak acid into the strong base. As weak acid conjugate base of the weak acid would be strong base too, in the terms of the conjugate base terms. We can also produce the acidic salt when we have a titration between strong acid to the weak base like this. Okay, for example, hydrochloric acid, when this is reacting with ammonia solution, that's strong and the weak, it produces that ammonium. So let's have a think about here. If we have ammonium NH4Cl solid here like this, when this is reacting with the water, let's think about it here. Denny, NH4 plus, NH4, or like an ammonium, would this be any of the conjugate base or acid? It's the conjugate acid of NH3. What is NH3 again? It's a weak base. So that's following to this over here then. We have a conjugate acid of the weak base. That means this is now working as a strong acid. Which means what? According to Bronsted-Lowry again too, which means this is now ready to donate a hydrogen ion. Does it make sense to all? Okay, so that means that it will now donate in the hydrogen ion too, so it becomes to ammonia, okay, leaving that hydronium ion and leaving the chloride ions. Now, we're not interested with the ammonia because it's weak, and we're not so interested about the chloride too because it's just the chloride, doesn't affect the pH. We're more interested about hydronium ion produced. What does it do? That means that because of we are adding some, after we're adding some acetic salt to that, we're producing a hydronium ion. First, it produces the more of the hydronium ion. In other words, it will decrease the pH as the concentration, the hydrogen ion is increased there. Okay, so if you have a question like determine whether that's acidic or basic or neutral salt, think about whether that's working as a conjugate base or acid or something. Okay, that's the key to solve the question, because there are so many questions in the trials and school practical tasks that asking you, we have something given, whether they determine that whether that's acidic, basic, or neutral salt. The answer is, and the way to find the answer is pretty simple. That just put it into the water, see what the products end up forming. Does it make sense to all? Okay. All right. In the case of this titration, we're using we tend to use the methyl orange because the equivalence point is lower than the 7. Yes.
Is the equivalence point in like strong something and weak something still the equal, like the point at which the ions are equal?
The ions are equals to. Even though, but the reason why we have to dominate more of the low pH and equivalence point is because of the property of the strength, that even after they neutralizing all the hydroxide ion represented there, they're still releasing the some hydrogen ion for the strong acid. Okay, or
not be equal anymore?
it's actually like in the point, we find the point where actually, in other words, the point where all that hydroxyl ion get neutralized by the hydrogen ion. Okay, so yes, it won't be equal, but we find a point where we can completely dissociating or completely removing all the hydroxide ion or hydrogen ion. That's be known as the neutralization point. Sorry, equivalence point. Okay, the last titration is weak acid and weak base titration. So as we discussed that before too, they are producing some neutral salt and have an equivalence point that's near 7, but we don't really do the titration, especially the volumetric analysis, because that changes the pH really dramatically. It's hard to determine that. So in this case, we do not use any indicators. Even if we do, we recommend to use the pH meters for that. So this is known as what? The volumetric analysis. We're using the pH meters to determine the neutralization or the equivalence point. Instead of using the pH meters then, we can also use something known as conductivity curve. So we have covered a little bit about conductivity. Conductivity in, when was that? Module 1 probably? Why the metals have the good electroconductivity and stuff like that too. Now, guys, just have a think about the word conductivity. Whenever you have word conductivity, there's terms related to electricity, but it's not a physics time. Let me just give you an easy example. It means that we have a good flows of the ions or the electron. I should say free ions and electrons. This is the key. If we have, so which means we have a greater concentration of ion, okay, that means that greater the conductivity. Simple as that. So what about the free ions we're talking about in acid and base? I'm talking about whether we have lots of the hydrogen ion or hydronium ion or the hydroxide ions. If we have lots of those available, we would say that's a high conductivity. Does it make sense? Because they are easy to flow due to that huge potential differences too. You don't have to worry about the physics for this type in here. Just try to understand or try to memorize that as higher, greater the concentration of the ions means greater the conductivity. That's the relationship. So in other words, concentration ion is kind of directly proportional to the conductivity. Okay, so you don't need to think too much about it. Just try to memorize that. Okay, that's kind of makes sense. Greater concentration, greater conductivity. That's it. Okay, so the conductivity solution can be depends on. It's good to highlight this. The type, identity of the ions, the type of ions that we have, the charge of the ions, the concentration of the ions, the mobility of the ions, and the temperature of the solutions too. It simply means that depends on size. If the ion size is big, like comparing that hydronium to the hydrogen, this is bigger than this, even though they have the same charges. This will be slower. this will be faster in terms of moving. Okay, so try to visualize that the greater the size means that they're moving really slow, and the smaller size moving faster too. But what we are interested here is this tool. So some of you, I think it's a Cullingford, you probably do the experiments related to conductivity. And this is the tool that you might use in the school. So we do the same thing, the titration. So we install the burette. We install it, but instead of the conical flux, we put it into the beaker, more likely, because we need to be on the bigger, like in the surface area. Instead of use the pH meters or the indicators, sometimes we do the indicators, we install that in the conductivity meter. So measuring the conductivity of the solution that you have in. So have a think about it here. If we have a start with a concentrated acid, I should say, strong acid, or the base. In terms of their characteristic and the strength, strong means what? 100% dissociation. They're ready to dissociate. They're ready to get ionized. They're ready to release their free ions. They tend to have greater conductivity. Okay, now, the point of the titration is again we want to determine the concentration of this. So what we do is we basically neutralizing that acid. So at the equivalence point, in other words, at the point of that you have a neutralization. Have a think about it here. Neutralization means that hydrogen ion is reacting with the hydroxide ion forming the water. Joanne, would water have a good conductivity then? No. It's a kind of misconception that the water has a good electric conductivity. In fact, the pure water doesn't have a good electric conductivity because it's not charged. It's not ion. So which means that at the equivalence point, you will see that there will be a decrease in the conductivity, or the minimum, the conductivity you will find it out. And as we increase the volume, you actually expect to see the increase in conductivity. That is described on next page, page 169, like this. So that conductivity curve showing you what? The titration between the acid, strong acid and strong base. You're seeing that we are putting some sodium hydroxide. So it started from this. This is representing by strong, concentrated, strong acid. The question is this, why that is showing in the high conductivity curve? The simple thing you need to remember is strong acid means 100% dissociation. There'll be lots of the free hydrogen ions available. Therefore, it has the greatest conductivity. So what happens as you put in the sodium hydroxide? You are gradually neutralizing it. And at the point, you see the minimum point. That is, they're fully neutralizing all the hydrogen ions available. So it's the point where all the hydrogen ions got neutralized to form water, H2O. What do you see that? You see that the minimum, the lowest point in the conductivity. So when we're looking for the lowest conductivity curve, that's basically representing the equivalence point in the pH conductivity curves. Then what happens here? Why is it increasing again? As you're adding some more sodium hydroxide, what happened? There will be more of the release of the hydroxide and sodium ions. Okay, means that we're now increasing the conductivity due to that greater amount of the hydroxide and sodium ions as you go in this section. See, that's for sodium hydroxide. We keep adding the sodium hydroxide over that too. So in here, we started with some hydrochloric acid, 0 sodium hydroxide, dropping down due to this getting neutralized gradually, fully neutralized, no hydrogen ions available, or no hydroxide even though, okay? And as we increase that volume, we get the more of these hydroxide and sodiums getting increased in that system too. Okay, so do not worry about what I mean by conductivity. So the simple things about conductivity is it's basically about concentration of free ions. In this case, we don't care about electrons, it's about free ions there. If you have a good flows with free ions, I would say that's a good conductivity too. Okay, so what about the conductivity curve between strong acid and a weak base? You would see something that's very similar in the beginning over here, because we started with the concentrated strong acid at the top. We started with this concentrated like HCl. So remember that, always refer back to the meaning of the strength of the acid means it's 100% releasing the hydrogen ion. But you would see what? At the new equivalence point, it will be 0. But this is because of what? Due to the weak adding of the weak base. And why the adding the weak base doesn't really affect the conductivity? Orion, why do you think like adding the weak base doesn't really affect the conductivity a lot?
I guess because it's a weak base, so it only partially ionizes, so it doesn't release that many like OH minus.
Or which is the free ions in this case. There's not much free ions available because, as you said, weak base means the partially dissociating. And when we're talking about partial again too, I'm talking about less than 1%. So it doesn't really, like, it's really insignificant in terms of like a released amount of the, the ions in the system here too. So this is the graph shape of the strong acid and the weak base conductivity or titration between two. So, but what you can find at an equivalence point is, this is the equivalence point. The point where you would see all that hydrogen ion from the hydrochloric acids got neutralized by the ammonia that we put it into. Does it make sense? Kind of, yep. Now, the opposite is this. We have a weak acid to the strong base. So what you see there here now is, we started from the weak acid. So this is the weak acid. And as you can see that, weak acid has the lowest, or lower the conductivity than the equivalence point. It's simply because they do not have much free ions available. Okay, remember that it always comes into form of the, so let's write it in here, acetic acid for example, if that helps you too. That means we don't have many of those products, they will keep in that form. It comes out, if I have like 1,000, maybe out of 1,000, 999 it comes out in this form, will be 1 and 1. So that means what? There's not many free ions available, therefore lower conductivity again too. But increasing the conductivity as you're adding up some strong base, as a result of that, you get the equivalence point. And at the point where all that hydrogen ion of the weak acids got neutralized, then you will see the sharp increase. Due to that, again, what? Strong base is now releasing the sodium and lots of the free ions in that solutions too. Does it make sense to all? Okay. All right, last one is weak acid and weak base conductivity curves. So you see that it's kind of interesting. We started from the low conductivity curve over here, okay? And it's gradually increasing up to the equivalence point. And at the equivalence point, you don't see much change in the conductivity in the same reason because we're dealing with the weak and weak. Okay, so the type of question you can get from this conductivity curve is, we can ask you that, why the shape of the conductivity curves look like this? Why the shape look like this? This means that it will be minimum 3 marks. You need to start from the starting point, why we have the lower conductivity. For that, you need to define the relation between conductivity to the free ion concentration. Okay, and you may need to define that what you mean by strong acid and strong base, or the strength of the acid and bases. Then you can start from this point that has a lower conductivity representing what? Due to the partial dissociating power of the weak acid or base, there are not many free ions available, therefore represented in low conductivity. Gradual increase from the neutralizations means that increasing amount of the free ions up to the equivalence point. From the equivalence point there, what happened? There will be an addition of the weak bases again too, which means there will be not much free ions available. Therefore, conductivity will be kind of gradually the same. Okay, that'll be on your 3 marks question though. But you got to think about how to answer the question. You probably need to provide some background, some information to support your answer. Okay. So let's do some exercise. Page 173, please, in class exercise 4.8. Use the information provided in the following titration curve to answer 1 to 6. So 1, identify the combination between of the strong and the weak acid and base, and the bases used to generate the 4 titration curve. So let's have a think about here. This is by looking at that, or probably the easiest way to have a look at the type of titration is look at the equivalence point. Okay, we have an equivalence point which is at 7. So highly likely this is what? Strong acid and a strong base straight away. What about this? We have an equivalence point is greater than 7. Then it would be strong base and the weak acid. Now, we had to start from titrate here. So have a think about it. We started from the lower pH, means that do you remember that? We put it into titrant and analyte. Put it in the titrant and the analyte. Okay, that means in this case here, as we insert in the pH meter over here, we start your analyte or your solution in your conical flask must be acid, not the base. Okay, we do not measure the pH of the solution in the burette because we already know the concentration of it. We call that as standard solution. We made it last week. So that means that we are analyzing the acid or the concentration acid in this case. Okay, what about this one? The equivalence point is lower than 7, indicating what? This is a strong acid plus weak base. Then lastly, this is weak acid then, the weak base then. Easy. Okay, 2. What is the concentration of the strong acid used in these titrations? Concentrations, okay. Assume that they are all monoprotics. Concentration, how do you find the concentration? Let's go for question 2A. So what you have to start from is, you started from their initial concentration of the initial pH. Remember that pH is founded by minus log 10 of the hydronium ion, okay, or same as the minus log 10 of the hydrogen ion, like this. So if you want to find that hydronium ion, or hydroxide hydrogen ion, same thing, let's write that, just in this case. That would be what? 10 to the power minus pH of that. So you're given, this is, graph A is strong acid. So it's B a monoprotic, just releasing 1 hydrogen, which means we can take that as, for 1A, would it be? The pH of that is given as 1. Therefore, its concentration must be concentration of the acid, HA, which is same as the hydronium ion. That would be what? 10 to the power minus 1 mole per liter. This would be the concentration of this strong acid. Okay? Now, what is the concentration of strong acid used in these titrations? So this is the only strong acid that we have, A and C. I can't do the same process for B and D. Why? Those are the weak acids. If I want to know the concentration of the acid, I need to know their Ka or pKa values. So remember that we can only use that. We can only use that for strong acid only. Three, what is the pH of the equivalence point for the titration shown in the graph A? So that's easy. That's basically pH at 7 is the answer. 4, explain why the pH of the equivalence point in C is different to the equivalence point in A, C and A. Okay. Why is it different? Why is the pH is a little bit less than 7? Because it's a titration between the strong acid and the weak base. So at the equivalence point, after we neutralize all the hydroxide ions, there will be still excess hydrogen. There will be still excess. So let's write it down. At 4C, at the equivalence point, there are excess hydrogen ions left due to the strength of the acid. Does that make sense? Neutralization point means that you use it up all that given all the available hydroxide ion, all that so even after they neutralize all the hydroxide ion, because it's a strong acid, they're still releasing that hydrogen ion, which means lower pH than 7 for equivalence point. Does that make sense? Eddie?
Yeah.
Did he kind of make sense? Confused?
Yeah, but then why wouldn't you just add more base?
There's no point of adding more bases though, because base would be weak base, which means we'll be limited. If we want to neutralize that with a weak base, we have to use quite a lot batch of the bases, because it's like only out of 1,000, only one release the hydroxide ion. So, which means if we have a given amount of the hydroxide and this here, we will be actually using all that into the given amount. So we get excess of the hydrogen ions too. Okay, so yeah, it's a bit odd in terms of equivalence point. Okay, this kind of makes sense about strength, acid, and bases. 5. Why is it not possible to accurately determine the equivalence point from the curve D? Why is that? Because this is the weak acid and weak base titration, and as a property of the weak base and acid, they'll be partially dissociating. So it is unable to determine the exact equivalence point due to the property of the weak acid and base, which is what? They're partially dissociating. Or you can write it down as 5 due to the property of weak acid and base that partially dissociating with the water, it's kind of unable, or it is extremely difficult to determine the exact amount of the ions released in the neutralizer in that reaction. It's like, yeah, I would say like a 1 out of 1,000 is coming out, but sometimes it could be a 2. It really depends, situation really depends too. So sometimes it depends on the temperature, depends on the experimental conditions, it can be varied too. So it's quite sensitive to measure the exact. But what we know about strong acid and base, it's always 100%. It's less sensitive than those weak, so it's much easier to control that because we know it's 100% all the times. Okay, 6. What would be the indicators used to provide a sharp endpoint for each of the titration separately represented by curves A, B, C? So again, endpoint means the point where you see the permanent color change in the indicator. So started from the A, preferably we can use the bromothiamine blue. That has a change from the yellow to blue, yellow to green to blue, or phenolphthalein if you don't have any options, but prefer that, as we know the clear color change. B, what would be the good indicators for that titration? As equivalence point is greater than 7, we would use the phenolphthalein that has the pH range between 8.2 to 10. C, we would use a methyl orange, or methyl orange that will change from the yellow to the orange too, because it will have because methyl orange has pH range between 4.5 to 7, 6 actually. And we do not use the indicator for the D type, generally using the digital pH meters to exactly determine the pH range. It's all given in your workbook, by the way. Okay, let's go quickly on try yourself questions. We're gonna just go through the answers together. You don't just copy the answers as we go. So try yourself, page 175, please. Question 1. What information is provided by the following titration and the conductivity curves? Let's start from A. Simply, what is this? What is the titration? What type of titration it is? This is strong base, and how do we know? Above 7. So equivalence point is above 7. How do we determine equivalence point? Okay, in this case, you're given the equivalence point over here. Remember that equivalence point is the where you get the equal distance in that middle region there. This is how we can determine equivalence point, and sometimes you need to show that in the graphing questions too. Okay, so equivalence point is greater than 7, indicating what? We have a greater amount of the hydrogen ion at the equivalence point. That's representing the presence of strong acid. Also, that pH close to 14. Sorry, strong base. What am I saying? Strong base. Okay, strong base and the weak acid there. Okay, the pH close to 14, representing that this could be strong base. As the higher concentration, we have the great, like the higher pH values too. Also, that point over here, so 3 points, 1, 2, and 3. So we talked about that and that. Last point, at the end of the titration, the pH will remain near at 7, representing that this is showing the weak acid property too. What about the next one? Question 2. This is the B. We also have 3 points, starting, mid, and end, starting, mid, and end. First, start from that high conductivity in the beginning of the titration, representing what? This is the strong, but as we add in sodium hydroxide there, that means strong acid. Must be presented there. How do we determine whether it's acid or base? Look at what you're adding. We're adding that sodium hydroxide in your burette, so your analyte must be the acid in this case. So having a strong acid means what? It's 100% dissociating, means that there'll be a greater amount of greater concentration of the free ions, which is greater like hydrogen ion in this case, therefore greater conductivity. What happens at the equivalence point? All the hydrogen ion now got neutralized with the sodium hydroxide, therefore decreasing the conductivity due to lack of the free ions. Lastly, what happened? Sharply increasing the conductivity is due to that release of the sodium and hydroxide as we're adding more of those bases. Does it make sense to all? Okay, so this is how you can interpret the conductivity curve then. We kind of did that in the class, so I'll skip that for now. Question 2. Let's outline the differences between the conductivity curve and volumetric. So, guys, when do you think, there could be a situation that we prefer to use conductivity titration than the volumetric titration. What would be the purpose? Like, would it be using the conductivity titration then? When is good time to use the conductivity over the volumetric analysis? Weak acid and weak base. That'll be one case. Okay. What about this? For the volumetric titrations, we always need to use the colored indicator. This is a pros of the volumetric analysis, in the same time cons. What if you have a solution that is a little bit colored? Like we use the colorless like acid and base. What if we use a titration of permanganate or the cobalt chloride, which is the colors of the blue or the purple? Putting that into phenolphthalein there, if we want to measure the pH, it's hard to determine the colors. So, changing colors means that in a case we have the 4 colored solutions, okay, we tend to use conductivity over then the volumetric analysis. We probably have the questions about this, but just write it down in here. Okay. Also that weak acid and base, we prefer to use the conductivity over the volumetric. So which means we don't have to use the indicator to determine the colors. Some cases, did somebody get like some cloudy, like some precipitate in your solutions too? Yeah. In a case you have some cloudiness due to some contamination whatsoever, or some cloudy solutions, or the precipitations. In a case you have a precipitation occurred there too, we sometimes prefer to use the conductivity curve because it doesn't really affect the conductivity in the presence of the cloudiness. But determining the color in the volumetric analysis is something that's very critical. That means that you can have the slightly different values because you have a cloud, like some kind of, the colors being kind of mixed or merged. Okay, so that's actually question 3, by the way. I'm sorry. Yeah, so that's the answer for the question 3. The why we're using over that. Okay, we can also use for more. So that's it. Sorry, this is the answer for question 3. I got confused with the questions too, but copy it down. What about we using something that super diluted? Have a think about it here. Conductivity is defined. It depends on that flows of the ions, or it depends on. It depends on more on the strength of the acid and base. Yes, greater concentration have the greater conductivity too. Means that we can use for the very diluted solutions. Saying 0.001 molar hydrochloric acid, sometimes it's really hard to determine its exact pH value using the volumetric analysis. So a conductivity curve would be actually better in terms of determining the points. Okay, so in these cases, we are using the conductivity titration over the volumetric with the indicators. Yes?
For diluted, do we still need like a more precise conductivity from the...
We might use, conductivity generally, because it also depends on shapes of the conductivity curve too. We actually get the graph of that too. That means using the volumetric analysis is more like plotting the data altogether. Or you can actually get the data too, but it will be really short and really small data. But in the conductivity curve, you can clearly see the sharp point or the minimum point of the equivalence point. So in that case, we prefer to use the conductivity.
Could you repeat what you said for the diluted solution part?
Diluted solution there. So think about here, if you have 0.001 molar of the hydrochloric acid, okay? How much of, if I'm using 0.1 molar sodium hydroxide, let's not do the calculation here, okay? That's your standard solutions, but that's what you want to get. How much of those is required? Maybe a single drop. A drop of the sodium hydroxide of this concentration can change the colors like straight away. Do you remember that a single drop of the sodium hydroxide you put it in can change the color like dramatically too? A single drop or less than a single drop can actually change the colors due to that low concentration. So in this case, it is unable to read a change in volumes too. So we prefer that using some conductivity curve because it shows a clear point, which is the equivalence point from the conductivity curve. Make sense? Okay. Yeah, so it's kind of manual things. All right. Could you try, let's make the standard solutions kind of practice we did. Could you try questions 6 and 7, please, now, please? 6 and 7. Yes?
And then what's like the circumstances in which your volumetric is favorable?
In a case of the, it's about the price. Conductivity, it's quite expensive to get the tools itself too. So not many schools actually having that. I know Carlingford, you guys do. You guys probably have to do some experiment with that too. But you only have 1 or 2 machines. So volumetric is affordable. It's a price matter. I tried to get one, but it's like $5,000 for the Connect something. So I gave it up. But in terms of the in university labs, we actually use lots of the conductivity titrations because they can afford that and it's more accurate. Try 6 and 7 now, please. Okay, let's go through the question 6 and 7. All right. The following titrates were obtained when the solution of the sulfuric acid was titrated against a standard solution of the potassium hydroxide. So we have okay, there are 1, 2, 3, 4, 5 the volumes available. Let's calculate the average for the analytic calculation here. So first thing you need to start here is find the midpoint or the median. Okay, so looking at those values here, or you can think about like what would be the outliers in this case. The median is somewhere between those 5.46 to 42. That'll be the medians, like a middle values too. So I'll accept these as kind of median. Okay, that means from the decimal point of that, it'll be plus minus 0.05 from that point. So taking this as a median 42, then plus 0 point means that 25.42, the range to 25.47 or to the 25.37 up to that range is the only accepted range theoretically. Okay, because we take that the last decimal points plus minus or last decimal points plus minus of that too. Okay, and which means accessing these three only. This is out of the range. Out of the range. Find the average of the three values only. Then you to get showing the working out. Question 6 plus 25.38 plus 25.42 divided by 3. Then you to get 25.42 milliliters in the average of those. That's a theoretical, by the way. As we did the practice last week, you would see like some ranges will be somewhere from the 7 to 2, 7 to 3. So it is very important to you controlling that last drop in a really slow rate so that we can get the good range of the data within 0.05 or 0.04. Generally, the burette is measuring up to the 0.1, so 1 decimal point. I mean, you can't really measure up to the 2 decimal points using the burette because it's an analog. So, which means it will have an uncertainty of the 0.05. So if you have 4.0 for the median values, it'll be plus minus 0.5 of that in good range of your burette. So that means if you have a 4 in the median, it'll be somewhere between 3.5 to 5.0, whatever the range that we're accepting. Okay, some practical skills test related questions. 7. Explain the differences between, first, a standard solution and a primary standard. Let's start from the A, standard and primary standards. So, standard solution is kind of more general terms that, let's write it down as standard, what the standard solution is. Standard solution is, this is a solution that with the known concentration. So we know that a known concentration, non-concentration solution. We know the exact concentration of that, so this is why that's basically standard, how we define the standard solution too.
So it's unknown?
Oh, sorry, known. Oh, what was I saying? Unknown. Known. I was saying, speaking known, but it's writing unknown. Known concentration solution then, okay? So 0.1 molar sodium hydroxide, anything known that solution, then we do that, okay? Now, primary standard is something that's similar, because we know the solution of that, but primary standard is something that we use to dilute into the making into the further standard solution or secondary standard solution. So for example, I gave you the concentrated sodium hydroxide last week. Do you remember that? That's known as primary standard, which is super concentrated. So this should be it's a substance, write it down, it's a substance they use to make a standard solution. Okay, now few rules to be a standard solution on this primary standard. Primary, think about primary that. This is actually the most concentrated, we know what that is. So it needs to be first in the pure form. Pure form, it must come to the pure form itself. Means that with the known chemical formula, okay, and then can be stored without deteriorating, or can easily stored without any deteriorations. How to spell it out? Oration, or the contamination. Spelling contamination. It's another issue too, and non-reactive with the atmosphere, especially the moisture. Okay. Lastly, did I say like sodium hydroxide tablets are quite expensive? So you're using the sodium carbonate, they are cheap or affordable. But in this case, okay. And lastly, having the high molar mass, preferably. So these are the conditions to be our primary standards. So we discussed that why the sodium hydroxide tablet cannot be a primary standard, because first, they're expensive, they are quite highly reactive. Something that absorbing the water quickly in the atmosphere cannot be used as a primary standard, as we discussed last time. Okay, so that has to be anhydrous, or the that shouldn't be hygroscopic, in other words, too. Okay, more like a practical task related. B. What is the difference between the equivalence point and the end point? Okay, generally when we say the equivalence point, again, let's write it down. Equivalence point. I mean, did I give you the definitions previously in here? Equivalence point in this page? Should have. You can actually copy that down. Equivalence point. Here you go. Okay, it's a point where they Oh no, don't worry about this. Yeah, this is poor definitions. Okay, let's write it down. This is a point, theoretical point where we get the when the concentration of hydroxide ion is same as the hydrogen ion is equal to hydroxide ions, or that's basically let's use this word. Using the stoichiometry, okay, the reaction ratio when the reactant amount is equal to the product, or the given product amount in stoichiometrically. That's how we can define the equivalence point as well too. Okay, and the end point is the point where you get when you're observing the permanent color change of the indicator. I have a feeling that I have a better definition at this point in here. If I find a better definition for the equivalence point, I will share that with you all too. Okay, because that's a little vague and it's only limited in like titration too. So acid-base titration. Okay, C. What about C? What's the difference between burette and pipette? You can visualize what the burette and pipette. So burette is something look like this, that you install that in your retort stand. Pipette is, we have thin, remember this, the pipette. Both of them have names quite similar, but they have a completely different purpose of using that. So a burette is a piece of glass, or it is a piece of the equipment that we use for what? Capable of accurately delivering a range of the volumes of the liquids. Okay, so generally up to 50 mils. It's generally what we use in the school lab. Okay, what about pipette? A pipette, spelling P-I-P-P-P-E-P-I-P-E-T-T-S, P-I-T-T-E-S, pipette. A pipette is usually delivers only a fixed volume of the liquid. Pipette, just think of it here. Pipette doesn't have any tap. It has the certain volumes written down. So you remember, like it can be example like 25 mils or 10 mils. Depends on that, like in a fixed volume that you have to. Okay. Whereas burette is we fill it up. We control the tap to measure how much of the solution they'll use inside of that burette. That's the difference between pipette and the burette. Lastly, aliquot and the titree. Okay, when we say the aliquot, guys, it's good to know. Aliquot is something that you commonly see in chemistry, like in some testers too. Okay, aliquot is the volume of the liquid, delivered from, let's write it down in blue, a pipette. Okay, titree is volume of liquid delivered from a burette. That's the main difference between titree and aliquot. So we didn't say aliquot in your titration process. It's the aliquots that we're transferring from each of the fixed volume of the pipettes then. Okay, so that's giving you some ideas about some volumetric titration, giving some more ideas about how to deal with those, in the practice. We'll have a chance to talk about vec titration later on too. Any questions up to here? Nope. Okay, so that's related to your homework last week. So basically everything there. Let's have a break, and we're going to come back with chapter 5, do some calculations. Buffers there. you want some lollies? Let's get to and show. Okay. Jones, do you want some lollies? Let's get them. You sure? Jenny, okay. That helps you to wake you up then. Grab something. All right. Chapter 5. Let's start. So, the last chapter of Module 6, and we're done. We're done. But but you realize this is the thickest chapter ever, and I probably need to explain you about buffers again next week or week after or prior to trials in the HSC, because this is not the easy content to understand in a day or maybe in an hour. If you can, that'd be great. I mean, you don't have to come back for the buffers, but what I'm saying by it is really the most confusing point is it's a mix of everything, every content we learned throughout chapter 1 to chapter 4 in module 6. So it's not only about 1 or 2, it's actually everything inside that too. So I picked this as one of the hardest topic in module 6 and probably whole year 12 too. But once you get it, it's actually help you to make sense to you. All right. Page 198, please. Let's quickly revising that what do you mean by Ka and pKa, so as we did before too. So if you remember that the K stands for something that equilibrium constant, and that we only can have that. Okay, so I mean this is something that you missed in the module 5 and 6, so if you don't understand the point, it's okay. We're gonna come back and kind of make this up to you. But rest of you, we've been doing lots of the equilibrium constant and Ka too. It simply means that find the ratio between the product's concentration of the reactant concentration. Do you remember this? Okay, and we define that K value when its K is high, K is low. When we have a K is greater than 10 to the power 4, we tend to say, oh, at the equilibrium, there will be like lots of the products available. Okay, I would say when the K is less than 10 to the power minus 4, and let's say at the equilibrium, this is actually a key word, there will be lots of the reactants available as well too. Okay, so in terms of, we can think about it as actually giving you some ideas about ratio between the product and the reactant at the equilibrium. So we use that to kind of extend the ideas to the Ka, which is also known as the acid constant, or the Kb, the base constant. So do you remember that? The pH wasn't the direct measurements for the strength. We can only use the pH to measure the strength when we have the same concentrations of the acid and bases. But something like Ka, which is acid constant, would be giving you some direct measurement of the strength of the acid and base. In other words, having the greater Ka means that, let's reinterpret that again too. As we're dealing with the acid constant, always the products of the acid would be what? The hydronium ion. That means that having the greater concentration of the hydronium ion at the equilibrium, more likely, therefore telling you what? Higher the strength of the acid. Now, Ka value sometimes be something really high, the large value like 10 to the power 18, 12. I don't like to use those 10 to the power some values, so instead of using the Ka, we're using something known as pKa, that is minus log 10 of the Ka value. P always stands for the minus log 10, like a pH stands for minus log 10 of the hydrogen ion. As we do so, you will see that higher the Ka, giving you that lower the pKa there. So it gives you a relationship that greater the Ka, higher the Ka, Give you the lower the pKa value, they're representing that, greater the concentration of the hydrogen ions, therefore representing that greater strength. The same as lower the pH, which I tend to say it's more acidic. Okay? A higher the pH, say more basic in terms of that. Again, think about a relationship. So, giving you some example of the Ka for some various acid and bases on the table given here. Table 1, you see that ethanoic acid, that's basically acetic acid too, has 1.7 times 10 to the power minus 5. That's relatively, it's actually really weak in terms of a really small value. So pKa is relatively high, that's a weak acid, and nitric acid started from that has Ka of 20. This is really high value. So put it into the log, you actually get the negative values too. That's representing that this is strong. And sulfuric acid is even go for 10 to the power 9 to the Ka. So you just see pKa of the minus 9. That's representing there's a strong acid too. Okay. We do the same thing for the Kb. That Kb would be then a base constant. So you can think of a Kb is the base constant, which means it's also be a direct measurements of the strength of that. So have a think about a relation here. Greater Kb means that lower the pKb value. That means greater the strength of the base constant too, or the base strength in there. Okay, or we can think about greater the amount of the hydroxide ion kind of dissociated or like ionized in this case. Pretty easy. Okay, let's do some practice question to using that Ka constants too. And we did that percentage dissociation. That's counting that how many of those acids can be presented to. So let's do the questions related to this. We did the kind of same question before too. Let's do it again. 5.1, please. All right. The Ka of the ethanoic acid is 1.7 times 10 to the power minus 5. So for a 0.5 molar ethanoic acid solution, calculate the pKa, so 5.1. Let's start off here. Let's calculate the pKa value. So Ka is given as the 1.7, so pKa, that is minus log 10 of the, given the value 1.7 times 10 to the power minus 5. Okay, Danny, how many sigfigs in the Ka given? So, how many decimal points do you think we need to show? It would be 2 decimal, which is 4.76. This is 2 sigfigs. Reason is, yes, you're right. It's P. 7 is it 7.7? Okay, yeah. 7.7. Okay, 7.7. So remember that for the pH and pKa, as we're dealing with the logarithm or the log, you only count that to the numbers after the point, the decimal point, is counted as sigfigs. We ignore that as we don't really count as sigfigs or pH. Remember this. This is the marking point that you lose quite a lot of marks in the exam and this practical task too. B, calculate the pH of that. Okay. Let's write it down, the ethanoic acid. So CH3, this is actually acetic acid, aqueous, reacting with the water. Okay, all right. To show the weak acid, make sure you put in the double arrows representing that this is a weak acid. Giving you this acetate and hydronium ion goes like this here. Yes?
So now if it's like a weak and strong acid, do we have to just memorize which acid is weak and which acid is
Yeah,
strong?
you only need to memorize which is strong, and the rest of those are weak. Yeah. There will only be like 3 acids you need to memorize for the strong acid, which is hydrochloric, sulfuric, and nitric. Only 3. Rest would be weak. Okay. Oh, you can see from the Ka value here, 4.77. What can you tell? That's a high pKa value. Therefore, the weaker, or the weak, the acid there. Okay, what we do here is we construct the ice table from here. We're going to use lots of ice table, by the way. So I mean, again, you haven't learned that before. Okay, so just copy this down. I will explain that on Thursday about the Ka. All right, for the water that's in the same pure liquid state, we ignore those. Initially, think about what you give it. Initially, you give it 0.5 molar or mole per liter. Okay, and initially you had none of those before because it's right before we put it into the water. Does it make sense to all? As a result of those equilibrium, the reaction, there will be change of minus x and plus x like that, giving you leaving the x and x, that will be 0.5 minus x. Now, in a case of that, you see the Ka value is less than 10 to the power minus 4 in this case. We take that, this is approximately 0.5. As the 0.5 is significantly greater than x, we kind of make assumption. Otherwise, you have to deal with the quadratic. Okay, yes, there could be a case you might need to deal with the quadratic, but not for now. So what do you have? Ka expression is then shown as acetate times the hydronium ion, that divided by acetic acid, and we have ignored that water because water doesn't have any concentration. It means that you get x squared on 0.5. That is given a Ka value of what? 1.7 times 10 to the power minus 5 here like this. Okay, as a result of that, you get the x is square of this 1.7 times 10 to the power minus 5, that times 0.5, and square root of this, you get 0.00292 mole per liter. This is the same as what concentration of the hydronium ion. Also be same as the acetic acid, acetate. Let's remain there too, which I found an x at the equilibrium. Therefore, pH is found from minus log 10 of the hydronium ion that you had. That is, putting that value, so minus log 10, you get 2.5354 actually, 54 in 266. Okay, let's find the percentage dissociation from here then. C, let's actually see. Any questions up to this point? Find the pH? Yep. All right. From here, to find the percentage dissociation, this means what? In what percentage of the acetic acid will release the hydrogen ion? That's meaning of the percentage dissociation. This can be found by A minus on HA, that times 100%. Okay, that is what? A minus, as we have acetic acid, that is same as 0.00292, divided by, given that HA of the 0.5, that's 0.5 times 100%. So 0.00292 divided by 0.5, then times the 100, you're to get 0.584. I just leave the 0.58% in 262. This means what? Only 0.58% of the acetic acid will release the hydrogen ion. Only 0.58%. Does that make sense? To all, kind of did the question previously in the calculation type, good revisions, but we're going to use these techniques again to explain, and I use that for the buffer. All right. Now, let's skip that for now. Could you try 5.3 and 5.4 for now, please, then? I mean, see you on Thursday. See you on Thursday for this. You will need a help. As I said, this is a combination of everything we learned throughout the module 6, so and a bit of module 5 as well. So you won't get that for this term. You will get these, but in next term. So you have a term to catch that up and kind of prepare. So don't get stressed about this module 6 for now too much, okay? Focus more onto the module 7 that you learned in school. More likely you get some report writing about the module 7. If you do, let me know. And we're going to start module 7 quite quick at the end of February. So we're going to cover out all the contents you're doing in the school as well too. And module 8, I hope you don't do the module 8. I hope you move back to the module 5 straight away. But let's see. Okay, let me know if you do start in module 8, then we need to cover a bit of module 8 as well too. Yeah, probably just up to like a few contents. They can't cover, they can't finish everything because you needed some background knowledge of this and some acid and bases to understand fully about some analysis of the organic and inorganic compounds too. Maybe they're going up to the some how to analyze the organic compounds. Maybe up to that. So that's up to where you can up to like for your trials too. Yeah, I don't know why they're keeping that still. I'm sure people are complaining about it quite a lot from 19. Finished! How to write the equation? Okay. Propanoic acid. Oh, those of you taking organic chemistry, you should know how to write the propanoic acid, by the way. So it always comes from COOH as releasing that. So I think about acetate. So when the propanoic acid, CH2, COOH, is reacting with the water, it will be like releasing the hydrogen ion always. So releasing the hydrogen from that, it becomes 2. CH3, CH2, COO minus, and it becomes to hydronium ion, just like the acetic acid or ethanoic acid too. Okay, so that is known as propanoate. Okay, but do we need this? We do. Now, what you have given for 5.3 is you're given the pH, not the Ka value. We need to find out what the Ka is. So let's construct that into the I's table that we may think about, okay, start off with the 0.05 molar of the acetic propanoic acid is given. Ignore the water, okay, and initially we had a 0 and 0 here like that. Then the change would be the same as before. We get the plus x, and x. That'd be minus x or 0.05 minus x. Approximately, let's make it into easy, simple form of that, because we'd assume that this would be a greater, significantly greater than the x value here due to that smaller Ka value. We take that as kind of assumption. Okay, or you may solve the quadratic. You can, you're solving from here, but it shouldn't be a bigger issue. Okay, now, what we know from there is the pH of this solution is given as 3.09. That means we are able to find the concentration of the hydronium ion from the pH by 10 to the minus pH. That is 10 to the power of the minus 3.09 here like this, mole per liter. Okay, this is then same as this one, which is same as then X. That means the same as the CH3, CH2, COO minus concentration as well. Then showing the Ka expression from it, that is showing the propanoate times that hydronium ion divided by CH3, CH2, COOH. Then you might need to do that what? We did the 10 to the power minus 3.09 square divided by 0.05 like this. Calculate it correctly, then you should get 10 to the power of the minus 3.09, and the square of that divided by 0.05, you should get 1.32 times 10 to the power of the minus 5 for the Ka value. Okay, got it? That's how you can think about like in this question. It's kind of going backwards from the Einstein table from the previous question too. So remember that pH is always referring to the amount of the hydronium ion in that equilibrium state. 5.4. Write the dissociation equation and Ka expression for following acids. So dissociation equation means that you got to think about what happens to this when this is reacting with the water. So start off from the NH4, ammonium. Again, ammonium is what? Conjugate acid of the weak base, which is a conjugate acid of the ammonia. Okay, how to determine whether the conjugate acid and base? Think about whether the ammonia can accept more hydrogen or not. Okay, ammonium cannot accept further more, but can lose to become ammonia. This is why you need to have some kind of data or something kind of saved data in your head. You've never seen the NH5 heavy. Okay, but you haven't seen the NH3 quite a lot in the examples too. So you got to think about, oh yeah, okay, so it must be some working as a base, acid, means that when it's reacting with the water, it would go like producing the NH3 and then leaving the hydronium ion like this. So relatively, it's working as a strong base, strong acid, but we can still find the Ka because there will be slightly small little errors there. So Ka expression for that is then NH3 concentration times that hydronium ion concentration divided by NH4 only. And we do not count the water because it's the pure substance. Yes?
We always assume it's aqueous, like in solution when we're told to write this.
But solution means aqueous.
No, but like,
Mm.
this question doesn't specify solution or
Mm.
aqueous and stuff. I just wrote like as just hydrogen ion.
It'll be about 95% of the solutions forms because we're generally mixing with the water to find the dissociation for values too. And ammonium itself, ammonium itself cannot come out in the forms of solid or gases too, because it must be combined with another metal, the non-metals, be solid, but ammonium, if you remember that, cannot form the precipitate due to the snap rule.
We write the arrow, right?
Yeah.
We have to write it slower now.
Oh, no, not for this case. It may be sure like in the double arrows, but we just take the Ka value would be significantly high. So that's kind of representing. That's like same for the strong acid too. We can do the same, but it will be something that's really small. HCOH. Okay, Joanne, would this be working as an acid or base? Question B. Just simply, would this be an acid or base? It's an acid. How do you know? COH. Very similar time we have the only COH. Something you're probably going to do in module 7 later on too. Whenever you see a COH, it looks like this. There's a carbonyl and OH. We call that as carboxylic acid. Well, a little taste of the module 7. You should know that. Okay. And the name of this is known as methanoic acid for T2. Don't worry, okay, Ashley, you will be okay. We're learning that, we're getting to the stage of how to name those and the game that give a structure or formula. But John, it's good to know anytime you get the COOH that's working as an acid, the name itself is the acid too, means that reacting with the water, you produce what? Proton donor. So it becomes 2. HCO minus. Okay, it's always the hydrogen from at the back, at the OH time here. So this is called the COO group then. Okay, and now becomes 2 hydronium ion there. So Ka expression or what is the Ka expression would be HCO minus times hydronium ion divided by HCOH like that too. But Joanne, it was actually telling you the acids, everything. Yeah, read. This is my read, please. Read the question. Okay, HCN would be all cyanide gas. Also working with the as an acid means that it would go like producing the hydronium ion and releasing that into the cyanide here. Okay, so Ka expression would be easy. The product times the product divided by HCN. That's it for question 3.8. Yes?
So it doesn't matter if you write COH minus, or do you have to write
We have to write the HCO minus. That's more like organic chemistry forms, that from this, the carbon would not lose the hydrogen, but it's more like oxygen to hydrogen. Again, if you remember the intermolecular forces, that's related. I told you, like, no, it will bother you, it will kind of nag you until you finish HCC about intermolecular. I'm actually saying the same thing to current year 11. Guys, you will get the intermolecular force again in Module 7. So now your turn, you will get those again. I'll spend some time to explain your intermolecular force later, okay? I can share the video. All right. Let's skip that. It's kind of easy K and pKa calculations. I'm not really worried about how to find K and pKa and rest of those questions now. Okay, so any questions about, like, some calculating Ka, pKa, pH, or what about using the ice table? Do you guys feel confident using the ice table now? Then let's do this. Assume that. Let's have a think about it in this case here. I'll give you a situation here. So I don't need this for now. Guys, assume that I have 100 mils of just pure water, H2O. So I prepared 100 mils in the beaker now. What I add in on the top here is I'm adding some hydrochloric acid, which is a strong acid, say it's 0.1 molar and 10 milliliter. So before I put the hydrochloric acid to there, you know the pH of the water is B7. Now, what I'm doing here is I'm adding some hydrochloric acid to there. So I'm doing something about this mixture. So let's calculate the pH of this. For strong acid only, remember the acid only, you know that concentration of the hydrochloric acid would be always same as the hydronium ion, or same as the hydrogen ion that, because what happened between hydrochloric acid is with the water, when I put this into there becomes the single arrows, that all that hydrochloric acid will be 100% dissociating. Remember, that means that releasing that into the form ionizing the water and release the chloride ions like this. So if I have 1 mole of that, you have 1 mole of those produced for the strong acid. Does that make sense? So this means that we need to find a new concentration of hydrochloric acid. From here, what do? That we are diluting it. You might think like, 10 mils, we put the 100 mils, we're kind of diluting that acid. So you got to find a new concentration using the dilution calculation. So C1V1 equals to C2V2, or the C1V1 over V2. That this case we have an initial concentration 0.1 times that 10 divided by, given that 110 for total volumes too. Then what you get as a result, you would get 0.1 times 10 divided by 110, you get 0.0091. Then pH would be simply be what? Minus log 10 of that, 0.0091. Then log that, you get 2.04 is the pH of this. So can we say, okay, the concentration is only be 0.0091 for the hydrochloric acid, but the pH is actually extremely low, close to 1. So that's because that all the acid, which is strong acid, kind of dissociating to release the hydrogen ion. And that's something we have to consider here. Now, I give a second situation. This time, we have the same 100 mils there. Okay, this time I have some 100 mils of the sodium acetate. Okay, let's say the concentration would be like somewhere like, I don't know, like 1.0 molar, really concentrated sodium acetate solution there. And what I do here is I do the same. I add the same amount of hydrochloric acid, which is 0.1 mole per liter, and 10 milliliter in here like that. Okay? Let's have a think about the reaction between these two. So when we're putting the hydrochloric acid into the sodium acetate, what happened? This is the conjugate base of the weak acid, so working as a base. It will accept the hydrogen from the hydrochloric acid, which is willing to. So there will be a reaction between two forming acetic acid is now formed, and they're leaving that sodium chloride, which is what? The neutral salt. Make sense up to here? Then how much of those will be produced? Let's have a think about it in here. And for this question, you actually need to use this. And of this HCl you're given can be found by CV. That is what? Given that 0.1 times 0.001, 0.01 mole of the hydrochloric acid is given. And of the sodium acetate can be found in the same method, CV, 100 mils and 0.1 molar. So that's what? 1 times 0.1 giving you 0.1 mole. So comparing these to what you see there is, we have lots of the sodium acetate compared that to the hydrochloric acid. So this is what? Your limiting reagent. So can we say the hydrochloric acid is the limiting? Do you remember we did this kind of questions in the practice before? This is all because of this. Limiting reagent. Therefore, what can you tell about amount of the acetic acid produced? Would it be same as that 0.001 mole over here? What would it be then concentration of the acetic acid? Can be found by N over V. This is 0.001 mole divided by total volume is now adding the 10 mils to 100 mils, 110, so 0.11. Giving you out that 0.001 divided by 0.11. Actually giving you this same 0.0091 mole per liter. But didn't we have that in here previously? Can we just simply say, if we have the hydrochloric acid, it's now what? When we have in the presence of sodium acetate, they are all like shifted, kind of swapped into the acetic acid as a result of the reaction between the hydrochloric acid to the sodium acetate. Does it make sense up to here? Then, let's use the Ka value of that acetic acid that we're given. Acetic acid, let's use the values that we're given. Where is it? Acetic acid. Okay, this has Ka, it will be given, of the 1.7 times 10 to the power minus 5. Then ask the same question. Can you find the pH of this? The question we just did, isn't it? That question would be that, for the acetic acid that we have now, go for the reaction. I show the full working out for now. Producing acetate and some ammonia, hydronium ions. Then what we have, ice, again, is exactly the same question we just did, that we're given 0.0091. Okay, assume that we have a certain concentration here too. Now, we can actually find the concentration here. That's a leftover amount of the acetate, which is from the sodium acetate there. So that would be 0.1 minus 0.01, that divided by 0.11. And this would be 0 initially. Do you guys get what I'm doing over here? I'm finding that we used to have this much of sodium acetate, which is the same as the acetate initially. Minus that is how much they can left over. So that's because they're reacted. So this is how much we get. The change would be then plus x minus x, and plus x minus x like this. Then you get 0.0091 minus x, and that, let's actually find the value. 0.1 minus 0.01 divided by 0.11 You get 0.9 plus x, and the x here like that. Can we just assume that this is approximately 0.0091? Assume this is approximately 0.9 then. Okay, then K, A expression would be CO minus times hydronium ion divided by acetic acid. That is what? 0.9 times x divided by 0.0091. That's given as 1.7 times 10 to the power minus 5. Then x is finding 1.7 times 10 to the power minus 5 times 0.0091 divided by 0.9. You get 1.72 times 10 to the power minus 7 mole per liter. What is this? This is the same as concentration, the hydronium ion. Can we find the pH from here? We can. Log of that, you get 6.76 is the pH of this acetic acid then. Let's pause for now, okay? I'll give you about 10 seconds to think about what we have done here. So first is, I just simply put the hydrochloric acid into the water. Yep, it's kind of diluted the acid. So you see that from the pH 7, it was pH 7. Now we have the pH of something like 2.04 dropped significantly. Because water is not really resisting to that strong acid, kind of invasion of strong acid. It will kind of dissociating to form all the hydronium ion. Now, in the presence of some sodium acetate in the water, in the given amount over here, what you now see there will be a reaction between not the water, the hydrochloric acid to the sodium acetate, producing the acetic acid, which means all that is now replaced into the acetic acid. So instead of we having the strong acid now, we now have some weak acid and some conjugate base of them. Does it make sense? Then, what does it do? Assume that the pH was 7 as well. Then, instead of changing the pH dramatically, we now see the pH is only being changed 6.67. So it's not that much compared to the first. This is called the buffering effect. That how the conjugate base, remember that the conjugate base, the weak base is working as strong base. How the conjugate base is reacting with the strong acid, so they're kind of resisting the change in pH values a lot. Does it kind of make sense to you? As I told you, this is the hardest topic, this is the hardest content to understand, but because I'm combining everything you learned from Module 5 to Module 6 for one topic here. To understand that, you need to understand what I mean by strong acid and weak acid, and you also need to fully understand what I mean by the K values. Calculation involving that, some dilution of the moles limiting reagent from Module 2, ice table Module 5, pH calculation in Module 6. So the buffer is the topic that people found at the hardest in whole HSC courses. They found it like, wow, I don't know where to start it from. I understand. So this is why I'm giving you some clue that let's start off step by step. For simple, like a mix of the acid or the base into the water, that's basically dilution. Okay, then we've done the question that find the pH or P or H of that. For this is the acid and base reaction or neutralization between the conjugate base of something to that. Therefore forming this. The point of this is we do not have any of the strong acid left over if we have more amount of the bases kind of inside there. Do you remember we did the kind of similar in the calculation question, the sodium hydroxide plus hydrochloric acid, and after mixing these two, what is the pH of that resultant solution to? It's somewhat very similar, but this case, instead of doing the strong and strong, I'm doing with the strong and the weak, kind of relatively weak, so that we have to use the Ka value to find this value. Does it make sense? Okay. So the effect of the introducing buffer is always that it's kind of damping down, it's kind of delaying that change in pH. And thinking about the swimming pool, that outdoor swimming pool, it's always, we said it's kind of buffered. We have to put in the buffering solution because after kind of rain like today, rain contains a bit of like a sulfuric acid in it. your swimming pool gotta be acidic, and you don't want to swim in the acidic pool. So there must be some chemicals that resisting the pH change so that you can safely jump into the pool after the rain. Okay, so swimming pool question is something what we had in 2022 HSC. I picked that question as one of the hardest questions in whole HSC history in terms of calculation. It's an interesting question, by the way, but people get confused about buffer and calculation questions. Okay, so this is the type of the buffers that we can think about here. So let's talk about then what the buffer is, or how to prepare the buffer solution. So when we say the buffer is something that it's a bit slow. Okay, page 207, please. So buffer, when we set the buffer solution, it's generally the, say, a mixture of weak acid and its conjugate base, or weak base and its conjugate acid is something we know conjugate acid there too. So let's think about how to prepare. So how do we prepare? How do we prepare the buffer solution? How do we make the buffer solution then? Okay. Technically, to make the buffer solution, the first method is you mix the weak acid solution to the conjugate base of that, conjugate base solution. What I mean is you prepare 100 mils of the 0.1 molar acetic acid. So you prepare that, okay? And you mix that with another 100 mils, maybe like a different volumes of 0.1 molar, same concentration, but this time it would be sodium acetate solution 2. So you prepare the two separate beakers, pour that with the one acetic acid, pour another with the conjugate base of that, mixing these two, and the resulting that is you get the 200 mils of the buffer solution that's mix of some CH3, COOH, as well as sodium acetate. Sorry, not the H, missing the H. COH is present both in that solution too. Okay, you're probably thinking about aren't those two are reacting towards each other, because then we know that these two are the conjugate acid and base relationship. So even after we mix them, they were not really going for the further reactions. They would come as kind of mixture. Remember that buffer is mixture. It's not a pure solution. It's a mix of acid and conjugate base, weak acid and conjugate base. So in this case here, we have both of the weak acid and conjugate base inside of the mixture. Okay, this is the first method. Okay, the second method to prepare the buffer solution. You pour, or like pour some strong base solution into the a weak acid solution too. This is how the second method to prepare the buffer solution too. So I'll show you what that means. Assume that we have say 200 mils of the acetic acid. and that's a 0.1 molar acetic acid here. Okay, what I do here is I'm adding some 50 mils of the 0.1 molar sodium hydroxide. Okay, now have a think about the consequences of that. As I'm putting some 50 mils 0.1, this is relatively, say, the N of the sodium hydroxide will always be less than N of the acetic acid. Okay, so we are technically making the sodium hydroxide be yaw in the limiting reagent. Then as a result of the reaction between sodium hydroxide and acetic acid, they're producing some sodium acetate, and the remainder would be water. What is this? The conjugate base of this weak acid. Means that the N of the sodium hydroxide in this case will be same as N of the sodium acetate that you want to make it inside there too. So as a result of that, what you're getting is you get 250 milliliter, as you're adding 200 mils to 50 mils, of that, some acetic acid remained and sodium acetate produced. And this is what? It's a mixture of the acid, weak acid, and conjugate base. This is the second method of making the buffer solution there. Okay, so the point of that the preparation is this amount of the strong base must be always be less than amount of the acetic acid you have. So we want to leave that, intentionally we want to leave a certain amount of the acetic acid so that it's kind of making as forms of the mixture as that. So remember the two methods. This is the more common, by the way, more common appears in the exams. That giving you that some equation, and people found like, oh, okay, what's the purpose of doing that? You have to notice that when the weak acids are reacting with a strong base, okay, they are more likely to form the buffer solution in the case that the strong base has less mole than the weak acid. Okay. Does it make sense to all? Okay, kind of makes sense. So first preparation, you prepare the same amount or different amount, but we just kind of mix that, make a mixture. Second method, prepare the some more amount, huge amount, more amount of the acetic acid, the weak acid. Pour that with the some small amount of the strong base, producing some conjugate base of it. So providing some buffer solution too, which is a mixture of the conjugate acid and conjugate base. Okay, does that make sense up to here? This is how we prepare. Then, let's think about how the buffers are functioning then. So let me just give you another things. So after this, let's assume that we prepare the 250 mils of the acetic acid and sodium acetate. A mix of that too. Now, think about what happens when we're adding some hydrochloric acid or having an invasion of hydrochloric acid. Alright, if I put some hydrochloric acid to this mixture, say this is a mixture, from these two, which will be welcoming, which will be reacting with hydrochloric acid first? Sodium acetate. So this will be now reacting with sodium acetate. And what would be the product of this? We have sodium acetate and weak acid. That means producing that sodium chloride, and we get the acetic acids now produced. Okay, so what's the consequences? So addition of any like a strong acid is now replaced into the substitution into the weak acid there. So instead of you adding the strong acid, now you're adding the weak acid there in the system there. So do you remember the property of the strong and the weak acid? This is 100% dissociation. So if you get these, you have a mass of the big blocks that are really strong, comes in, try to invade it into. So what the buffers do, what this buffer do is they're kind of replacing that, substituting that into the weaker. So instead of getting the stronger one, they're substituting into the weaker one and therefore minimizing the pH change, because we know that the weak acid, acetic acid, only has 0.58% of the percentage dissociation. This has 100%. So basically you are what? Substituting into the weaker so that what? Releasing the, kind of preventing the release of the hydrogen ion. So that means kind of preventing the release of the hydrogen ion from that as a result of that. This means what? This will preventing, or we call that buffering the pH change. Does it make sense to all up to this point here? As I say, I'm covering something that's very important, something that's very something that's so confused. What if then we're adding some sodium hydroxide here? Joanne, if I added some sodium hydroxide into this mixture, which one of those will be reacting with the sodium hydroxide? It's acetic acid. So let's think about the reaction between sodium hydroxide and the acetic acid. Okay, this will now working as acid and base. So sodium, acetate is formed. Yep, and water is formed too. Neutralization, salt and the water. Okay, so what we have now, we can see there is, we have some addition of the strong base into the systems. That means that what? You're getting the substitution into the weak base, or weaker base in this case. So because, yes, this is a strong base, but compared to sodium hydroxide, it's kind of weaker base. You're right, Ashley? Yeah, I know, yeah. I know, this is not easy to understand. Which means that what? Preventing the release of the hydroxide ion. That means that what? It's also doing some of the same work, the buffering the pH change again. Okay, this is how the buffers are functioning too. So it means that whether you have an invasion of the base or the acid, or like addition of the base and acid, because we have a mixture of the conjugate acid and some weak acid and conjugate base of that, they will like kind of resisting, kind of substituting into the weaker. So it's kind of represented in here as well too. The buffer solution, the equal mole in the acid and base. When you're adding some hydroxide, which is the base, what happens is the hydroxide will be reacting with the acid first. Therefore, it's releasing the acetate instead of the hydroxide. Now, acetate is known to be a weaker base than the hydroxide itself, so it's kind of what? Buffering means it's kind of minimizing the pH change. Okay, same thing has happened when we're adding some hydronium ions there, or like putting some acid into the system. It's increasing the basically the amount of the acetic acid, so kind of minimizing the change of that buffer. The pH of the solution too. Okay, now this is kind of theoretical. Let's do some actually some calculation. Okay, it's got to be a really long calculation, by the way. Okay, 5.6 please. Question A, B, and C. It will take about half an hour to actually give you all that explanation, so let's go through that. Okay, acetate buffers are used in the biochemical studies of the enzymes and other chemicals components of the cells to prevent the pH changes that might change the biochemical activities of these compounds. So, we have now mix of the 0.1 mole acetic acid and 0.1 mole sodium acetate. We're preparing two solutions, mixing them together. Okay, do you get the point over here? So you prepare the two, visualize that you prepare the 0.1 molar of the acetic acid and some sodium acetate. You kind of mix them together. And the question is asking you, after we mix them, what would be the result and the pH of those? So let's have a think about that. The Ka of this is given, acetic acid given as 1.8 times 10 to the power of the minus 5. It's a given, just write it down. Then we're going to think about the reaction between the actual acetic acid. When this is reacting with the water, it's releasing that acetate with some the hydronium ion, like this. Okay, write it down the state, AQ, liquid, AQ, and AQ here like that. What we can do is we're going to construct the ice table for the first one. That initially now you're given 0.1 molar. That's given because you prepared that. Initially you're also given 0.1 molar as well too. Okay. As a result of this reaction, you would say that minus x plus x and 0 plus x goes like this. So you always see there is you see the x and 0.1 plus x and 0.1 minus x there. Okay, now what we have to think from here is we got to take that. This is approximately 0.1. This is approximately 0.1 as 0.1 is significantly greater than the x value. Then Ka expression, which is the CH3COO minus times the hydronium ion divided by CH3COOH would it be then 0.1 times x divided by 0.1. You will see this will cancel out, giving you the Ka value of the 1.8 times 10 to the power minus 5. This is what? Same as the hydronium ion concentration. So the pH is simply the minus log 10 of that value. You're to get 4.74 for this mix, the buffer solution then. Oh, it's a given. It's a given, yeah. So, yeah, it should be given. Otherwise, we can't solve the question. Okay. Now, B. Calculate the pH after 1 milliliter of the 0.1 molar sodium hydroxide is added to the 100 mils of this buffer. Then, giving a solution with a volume of the 101 milliliters. So, what we have to do, you prepared the buffer solution by mixing two separated solutions now. Okay, now we have 100 mils of that. So what we do after is we're adding some sodium hydroxide into that. So we're going to determine the change of the pH from it. So what you have to think from here is when the sodium hydroxide is added, think about the consequences of those. This means that first of all, this will be reacting with sodium hydroxide. We'll be reacting with the acetate, also acetic acid. First of all there, and releasing that acetate or sodium acetate, if you want to say the sodium acetate, that's fine. And leaving that into the water, H2O liquids here like this. So let's have a think about the case here. This means that there will be decrease of the acetate. Let's write it here. This means decrease of the N of the acetate, acetic acid. Okay, increase of the N of the sodium acetate as a result of those the addings of sodium hydroxide in it. Does it make sense? Okay. Then what can you tell? Amount of the amount of the CH3COH decreased Wouldn't that be same as the amount of the sodium acetate increased? And this is what? The amount of the sodium hydroxide added. In other words, N of the sodium hydroxide that we added can be found as CV. From that, given the 0.01, 0.10 times 0.001, giving you out 0.0001 mole. If this many of the sodium hydroxide is added to this buffer solution, this will be reacting with acetic acid, which is what? This concentration, or this concentration 100 mils of those concentration there. Wouldn't that be same as the amount of the acetic acid reacted from that reaction ratio? Therefore, that would be same as amount of the sodium acetate produced as well too. You guys get up to this point? Yep. Then it's a matter of how much of the sodium acetate that we are given. So you were given that concentration is 0.1 molar. Okay? The concentration of the acetic acid in the previous solution that is given as same as sodium acetate, because we designed that to be the same concentration, is 0.1 molar. Yep. And in the volume is 100 ml initially. Then N of the acetate, acetic acid would be CV. That's what? 0.1 times 0.1, giving 0.01 mole was initially what we had. And N of the sodium acetate would be the same. That's 0.1 times 0.1, giving you 0.01 mole. This is something that we had initially. Okay. Any questions up to this point here? I've just found out how many of those acetic acid and acetate was presented in the given 100 mils, in 100 mils. Then, amount of the acetic acid is now in the final, at the equilibrium, or the final, I should say it's a final. The final is N of the acetic acid you're given minus N of the acetic acid that's reacted, which is 0.01 that's given minus that 0.0001 mole. It's the amount of this given there. Then you should get the value would be 0.0098. Let's find that. 0.001. You get 0.0099 mole. It's actually given. It's kind of left over. And N of the sodium acetate would be N of the sodium acetate you're given plus N of the sodium acetate produced. That is 0.01 plus 0.001. That's giving you 0.0101 mole. Okay, I'll pause that for now, for a bit, okay? Because I want you to understand what's going on in here. Remember that we're dealing with the mixture of acetic acid and sodium acetate. So when the sodium hydroxide kind of goes into that mixture, first, it will reacting with the acetic acid. Means that as these two are reacting each other, they will consume. So kind of decreasing the amount of the acetic acid. As a result of that, increasing the sodium acetate instead. So the amount of the sodium hydroxide we put it in would be equal amount to the acetic acid reacting with, same as the same amount of the sodium acetate produced too. This is what we have done in here. This means that this is the final amount of the sodium acetate now we have. This amount of the acetic acid now we have after the reaction with the sodium hydroxide. Okay, then We can find a new concentration of the acetic acid by C equals N over V, that is 0.0099. That divided by the volume is now beyond not 100 mils, it's 101 mils. So that'll be what? 0.101. So 0.0099 divided by 0.101, you'll get 0.098 mole per liter for the concentration of the acetic acid. For the sodium acetate, N over V, that'll be 0.0101 divided by 0.101, giving you 0.100 mole per liter. Okay, are we done? No, we need to find the pH from here again too. Means that we'll bring that back into this situation then again. That's the ice table. So, in this mixture now, we have acetic acid. It can be divided into the conjugate base of it, plus hydrogen ion here like this. Hydronium ion, same thing. Let's write it the hydronium ion, plus the water. We can skip that, put it into the ice table. Then initially now changing it into the 0.098. And this is 0.100. There's not much change. I mean, there's no change at all. And that would be 0.2. Okay, then you would get minus x, and plus x. Okay, so it would be 0.098 minus x, 0.1 plus x, and x. That's approximately 0.098, approximately 0.1, and that would be x2. So Ka expression here again means that it would be hydronium ion times the acetate divided by acetic acid at the equilibrium. That is 0.1 times x divided by 0.098. Again, Ka is given as 1.8 times 10 to the power minus 5. So the x would be 1.8 times 10 to the power minus 5. That times the 0.098 and divided by 0.1, you get 1.764 times 10 to the power minus 7 mole per liter. That's the same as concentration of the hydronium ion then. Then pH would be minus log of that. You get, finally, 6.75. What is the final answer? Oh, did I do something wrong? This shouldn't be. 1.8 times 10 to the power minus 5 times 0.098 divided by 0.1 and like that. Oh, yeah, sorry, 4.75 is the right answer. Yeah, calculation. 4.75 is the final answer. Whew. Now, compare. Before we put the sodium hydroxide, the pH of the mixture was 4.74. Okay? After we put in the sodium hydroxide now, you'll see that pH is increased by just 0.01. And this is how we can prove the buffers working quantitatively, the calculation methods. Yes, full of the working out, like some calculation, ice tables, Ka, but nothing's new, to be honest. Nothing new. You learned that. You learned that in your module 2. You learned in module 5, module 6. But as I said, it depends how we combine all the contents and making the harder questions. This is known as one of the hardest questions you can get. Because it's hard to think about, okay, adding some sodium hydroxide in the buffer means that we decrease the amount of the acetic acid, increasing the acetate. If you didn't notice that how the buffers are functioning, then you can't actually get up to the answer over here. And people are actually kind of confused about to find the concentration here again too, so they actually kind of didn't get the values right, so that pH would be quite wrong. But I just proved that quantitatively, like in the calculation, that pH of this buffer solution doesn't change a lot, even after put the sodium hydroxide in it. Let us compare to question C. for the comparison, calculate the pH of the 1 molar, 0.1 molar. I'm saying 1 ml of the 0.1 molar sodium hydroxide is added to 100 ml of solution, or the unbuffered solution with a pH of 4.74. Volume, and yeah, find that. Okay, let's do this question 2. I need a space for that. So this is the unbuffered solution, which is known as 1.8 times 10 to the power minus 4 molar solution of the hydrochloric acid. So what you're doing here is question C, hydrochloric acid is now reacting to sodium hydroxide. You add it, producing the sodium chloride, aqueous, and the water. Now, amount of the NaHCl given is a CV. That's a 1.8 times 10 to the power minus 5. That times the volume, which is 100 ml, so 0.1, giving you that 1.8 times 10 to the power minus 6 mole is the amount of the hydrochloric acid you're given. Then amount of the sodium hydroxide you're given is do the same way, CV. That's what? Amount 0.1 times the 1 milliliters, 0.01, giving you out that 0.01. That's 10 mils, 0.01. That's giving you 0.0001 mole of the sodium hydroxide is now added. Now, what happened between these two? These two are reacting to each other. Yep. And then we can think about which is your limiting reagent. Then all of those hydrochloric acids will be reacted, and then the remainder will be sodium hydroxide. So hydrochloric acid is, let's do that, the limiting reagent in this case. Then N of the sodium hydroxide that will be in excess can be found by N of the sodium hydroxide that is in given minus that N of the sodium hydroxide that's reacted. Okay, then we can find the N of the sodium hydroxide that's reacted, which will be same as the amount of the hydrochloric acid given. Because that's around the limiting reagent, isn't it? So we're given that 0.1. Therefore, N of sodium hydroxide in excess would it be the given amount of sodium hydroxide, that is 0.0001 minus that 1.8 times 10 to the power minus 6. That's giving you out the 9. Let's calculate the values. 9.8, okay, 0.0001 minus 1.8 times 10 to the power minus 6. You get 0.000982 mole will be given. Then concentration of sodium hydroxide will be given as N over V, that's 0.000982 divided by 101 mils, 0.101. And you'd get 9.72 times 10 to the power minus 4 mole per liter. But this is the same concentration of the hydroxide ion because it's a strong base. That means we can find the pOH from it. That is log that. Then you get the pOH would be 3.012. That's making the, okay. And then pH with 14 minus pOH. You get 10.98. Oh, that's huge. 99 in the two suffix. So that's the pH when the solution is not buffered. And that was the pH when the solution was buffered. I know, complicated. So I'll probably emphasize the word a lot when we learn the module 2. If you don't understand like a CV or N equals to CV or any of the dilutions, if you're not familiar with those calculations, you'll be in trouble in module 6 because of this. Okay? I think this is one of the hardest questions, by the way. Any questions about buffers? Unbuffered, buffered. Unbuffered, buffered. Do you need a break? You know, like break for your massage your brain a little bit. Okay. I give you a little time to like to breathe in and just get the rhythm back. But this is one of the questions that I picked the hardest. Okay, Henderson and Hertzsprung equation. Don't worry about this. Some schools learning that. I don't know why. This is the university level of the calculations. But I just put it in just in case. If you're learning that, let me know. If you do it, I can cover it. It's easier than what you thought, but it's mainly about these questions there. So. All right, don't worry about the Henderson-Hertzsprung. This is something that hard.
So is this the 2016 HSC question that you're talking about?
22.
Okay.
I show you that. I don't know. I don't want to discourage you by showing that. Okay, I quickly showed you what I mean by like one of the hardest questions that we had in HSC. Anyways, you got to do it. So. Question 34, 2022 HSC. This 4-marker question is somewhat that I found it difficult, interesting. It's a bit early to do this question yet because we need to understand about the buffers. But that's the question. So have a think about what I mean by from here that sodium hypochlorite is an active ingredient in pool chlorines. Hydrolysis, so that's basically what you're given. So have a think about here. OCl is working as the base. This is conjugate acid. So in that solution now, you have a buffer of the weak acid and conjugate base of it. So the question didn't actually give me the clue that this is actually buffered, different buffer solution there. So a constant for that is given at 3.33 times 10 to the power minus 7. Pool chlorine to be affected, the pH by different buffer at 7.5. And the hypochlorous acid concentration should be 1.3 times 10 to the power minus 4. So calculate the volume of the 2 molar sodium hypochlorite solution that needs to be added to 1 times 10 to the power 4 liter pools to meet the required solutions too. It's quite natural that you don't know what is going on in the question first of all. Okay, as I said, this is one of the hardest questions. Not only you, student who took the HSC in 2022, they're panicked. They were like, "Whoa, what the fuck?" They will literally say, "Oh." In the reading time, I could hear like, "Oh, oh," looking at each other like, "Oh, we're screwed." I could tell like they're pale after they come out of the exam. And by the way, chemistry was their last final HSC, so they were like, oh, crying after that and asking each other like how to do the bring me that questions and how to do the swimming pool question. And yeah, it was actually hard. And last year I said like it was easier than the year before because we didn't have the questions like this. Okay, guys, so do not worry about the question you can't do now. That's my recommendation. We gotta start from something that you can do, something you can definitely get the marks. Anyhow, you only need to get 80% or above 80% for the HSC questions too. Okay? Strategically, if you don't know how to do this question, think about try to get to 2 or 1 out of 2 out of 4. The band 6 students actually got a 3 out of 4, like from their average. We got the average for this question. That average is really low. It's only 15%. Yeah. So, but in later on next week probably we're gonna go through this question. Next week, yeah. It's actually the KEQ questions rather than some. It's more about understanding the situation. And John, this is what I mean. Like I don't want to discourage you by showing you that questions. So let's do the simple, easier question. In class exercise 5.8, please, page 216. Now, could you do this question then? Okay, let's find the pH, the buffer solutions. Yeah, I'll leave that working out, but.
뭐가 달라요? 아니,
Buffered? Unbuffered. What's the?
What did we do different?
What do we do different? What do you mean? you have to understand for question, this is B and C. Both of the question B and C, we added the same amount of the sodium hydroxide, exactly same amount. That is this amount in here, 0.001 mole. Okay. Now, one is buffered, means that it has a mix of some weak acid and base. So we prepare that. Prior to this question, we prepared the solution, buffer solutions, by mixing up 0.1 mole of the acetic acid, 0.1 mole of the sodium acetate. We did that, and we draw out 100 mils. Okay? Now, you have to understand that this is a mixture. It's not like a pure something kind of mixture, as in like they can be separated. So, in that mixture, when the sodium hydroxide comes in, it will first react with acetic acid in the mixture. So, as a result of that, it will sodium hydroxide reacting with acetic acid. Therefore, they will decrease the amount, or the amount of the acetic acid we had, increase the sodium acetate that we have increased that. So what we have done is we found the initial number of moles of the acetic acid and sodium acetate, and then we minus that amount of the reacted from that reaction to get the 0.099. We added up the amount of the sodium acetate produced to get this much over here. Now, the volume is now changed because we added extra 1 mil. Remember that the question was actually kind of telling you that it's added extra 1 mil there. You need to catch that. It's not 100 mil anymore. It's not 100 mil anymore. If we added an extra 1 mil, it becomes 0.101. Then, the concentration of the mixture is now changed into the 0.08, 0.098, and 0.100. You get this up to this point actually? Up to this point? That's after we put there some sodium hydroxide into that. Then, what we have to consider here is, this is now mix of those acetic acid and sodium acetate. Put it into the ice table to calculate the pH of that like this. If I just ask you, hey, can you find the pH of that? It shouldn't be like a big issue because we know how to construct the ice table, we know how to make the assumption, we know how to calculate pH from it. Okay, so if that confuses you now, go by sections. Go this section, understand what is going on in this section here, okay, and then move on to YR, I'm showing all the working out over here, and then finally up to here. I'm not using some fancy like a mathematical skills like a differentiation, integrations. Actually, we can do the differentiations later on, but we never do that in chemistry. I don't use that. I'm simply using all the terms and the contents you learned, but it's a matter of you understand what is going on in the situation. It's a matter of how to utilize those basic tools to solve the complicated questions like this. And this is why I picked the buffer questions as one of the hardest in the calculation questions. And students are afraid of the buffer questions so a lot. They're always asking me, so do you think we gotta get the buffer question trial? I'm like, my honest opinion is I hope you don't get, but there could be a chance. There could be a chance. So this is why we started early for the studying buffer, but as I said, this will bother you, this will kill you, this will neg you until you finish HSC. Until the day before the HSC, this will actually attacking you. Yeah? 5.8? Seems like Joanne's burnt out. Okay, so let's do up to this question for today, because I know it's quite overwhelming to understand all the buffers. It's not, as I said, let's take a time. Take your time to understand what you mean by buffers, how to prepare. Remember how to prepare the buffers and the functions of buffers and calculations. Good news. The percentage of getting the buffer calculation in trial is somewhat pretty low. I would say 10%. If I have 10 trial papers, only say one paper that having the buffer calculations. Really complicated calculation. This is why when the buffer calculation came out on 2022, students were panicked because they never done like many calculations in the buffers, and it means that it's a good news for everyone that everyone couldn't really do well in the buffer calculations again too. But it doesn't mean that we won't get it anymore. I still think like a chance of you getting buffer calculation in your trials and school exam will be lower than other type of questions. More likely you get questions about how we use the buffers in the nature systems, like CO2 or like hemoglobins and stuff like that. Okay, that will be something that you must memorize to prepare for some trial prior to trials. But it is very important that the current trends in the HSC is getting really calculation heavy. They love to put some really heavy calculation questions, just like these type of calculations. And sometimes titration calculation can be really, really harder than. So something, this is something that we're going to think about. Okay, but for now, let's do this. Okay, 5.8. A student prepares a buffer solution by dissolving 0.12 mole of the ammonia and 0.095 mole of the ammonium chloride in 250 ml of the distilled water. The Kb of the ammonia is 1.8 times 10 to the power minus 5. A. Calculate the pKa of the ammonium from here. So, if you remember the relation between K and Kb, that Ka times Kb is giving you the Kw, that's 10 to the power minus 14. It will be given on your formula sheet, but it's good to remember this. Means that Ka can be calculated from Kw divided by Kb. That is 10 to the power minus 14 divided by 1.8 times 10 to the power minus 5, which will provide you, give you 10 to the power minus 14 divided by 1.8 and divided by 10 to the power minus 5. You get 5.56 times 10 to the power minus 10 for the Ka value. Then pKa from here is pretty easy, is minus log of that. You get 9.25. So telling you what, this is what? This is relatively a weak acid from the high pKa values. Okay? Or like lower Ka values. You can use both. B. Find the pH of this buffer solution. Then we're given now Ka value. This is more important things we're going to use. Now, what we have given here is you haven't given that 0.12 sodium ammonia. So think about the concentration ammonia you're given. That can be found by N over V. The N is 0.12. Divided by the volume here is 250 ml. So giving you 0.25. 0.12 divided by 0.25. You get 0.48, 8 mole per liter, or say the mole, like this. The concentration of the ammonium chloride, which is what? Conjugate acid of the ammonia, would it be 0.095 divided by 0.25 here again too. So 3.8, 0.38. A molar is something that you give it initially. Remember that this is the amount that you're given initially. That means we need to construct the ice table. NH3 goes into the Kb, goes into NH4 plus, sorry, that should be with the water. Let's go like NH4Cl. Okay, let's think about it in terms of Ka, because we have to construct in the forms of Ka formulas, or you can use a Kb, but for the acid dissociation, that this is working as an acid. So NH4Cl with the water will be working as NH3, releasing the hydronium ion here like this. If you want to use a Kb, you go to opposite. You go to oppositely from here. But this means ice table is constructed from this side over here. NH4Cl, that's 0.38, that's given. NH3, 0.48. Water, we have nothing, but hydronium, 0. It'll make a change. That would be plus x, x, 0.48 plus x, minus x, 0.38, minus x like this. Approximately, this is 0.48, as x is significantly small. This is approximately 0.38 then. Then Ka expression would be the ammonia concentration times the hydronium concentration divided by NH4Cl. That's what? 0.48 x divided by 0.38. That's giving Ka 5.56 times 10 to the power minus 10. Then x would be 0.38 times 5.56 times 10 to the power minus 6. And that divided by 0.48, you get 4.407 times 10 to the power minus 7 mole per liter. This is the same as the amount of the concentration of the hydronium ion. Then pH from here, log of that, you get 5.36 is the final answer. Is it too complicated to think about the ice table from here? I mean, I just simply put the some values in the initial there. We know that there's not much change in going because they are basically in the week. So it's a matter of how to find the OH. You can do the same method for find the POH using the KB then. Okay? So actually, it's for you, it's a good practice from the ice table because we get ice table questions, but this is harder than what you get in the school exam. I can tell. Okay, and Orin, as I show you the questions in from your schools, this is harder than your school paper too. I know, but I'm also preparing some of the trial and HSC as well too. So the type of question you can possibly get. Carlingford, you won't get the harder questions than this. Don't worry. Okay, so this is the peak. This is like the maximum peak. Same for you, Cherrybrook. You won't get the Pennant Hills. No chance. Okay, and then your school paper is relatively easy. I mean, because I've got the papers and Carlingford and Cherrybrooks, not Cherrybrook, sorry, Pennant Hill will share the same paper this year, the trials, most likely. Doesn't mean I get the paper early, I can't get the paper early. They release the paper after, in near at the HSC. But we try to get the papers early so we can go through the questions after the trials. That's later on. All right, any questions? Long day. Tuesday, second day back, probably. So, homework for next week. Just a few buffer questions. And could I also collect the homeworks from you from last week? Thank you. Oh, no, gotcha. Chapter 4 homeworks, please. Thank you. Chapter 4 homeworks, thank you. And that's it for today. Next week, let's do some more calculations about the buffers and, okay, I'll actually try to give you some practical tasks. Let's push that to the week after because I want to practice, I want to finish up the chapter 5, the buffers first, and then move on to the practical tasks after, okay? So I will give you some more HSC questions about these chapters next week. So I'll do some HSC questions. That's it. See you all. Safe trip. Yes.
I lost the previous one.
Which is chapter 4. Bye.
I'm not sure because this is also chapter 4 homework. This is the one.
The one that I just gave you. Oh, probably the typo then. Yeah, it'll be a different question. So there should be chapter 5, not chapter 4. So you can just change that. Didn't get the homework from you. Oh, thank you. Thank you. All right. All right. Okay. How was it?
Yeah, this is pretty hard.
Yeah.
Like this part. This part was harder. The right side.
It's